Welcome to QuickTol's tutorial on performing a tolerance analysis. This is the first of a series of instructional videos geared toward making engineers proficient with both QTA and tolerance analyses. You can follow along with this tutorial if you download the tool at www.quicktol.com. Today we'll be using the premium version of the software, but there's also a free version available. There's even a trial of the premium version. You can find the link in the description box. So let's get started. Here I have a simple assembly. There are two circuit cards and a metal chassis. The boards are attached to either side of the chassis with washers and screws. Now, for simplicity's sake, we're only showing a few screws, but I think you get the point. Let's take a cross section through one of the screws and we can see the area that we're going to focus on for the tolerance analysis. If you look between the tips of the screws, there's a small gap. We'll go ahead and measure that gap. And we see it's only 25,000ths of an inch. So let us grab an image so that we can use this for our tolerance analysis. There we have it. And we'll take it over to Excel. Take it over to Excel, where we will use the QTA add-in. Now I've got it installed, that's why I have this tab up top. Now again, I'm using the premium version, but you can get away with the free version. It'll have many of the features that we're going to be using today. The first thing I'm going to do is enable QTA, and this is going to give me access to all of the menus, and then I'm going to click create new analysis, and now I have a format that I can use. So the first thing I'm going to do once I get this format up is I'm going to want to name the analysis that we're getting ready to do. So I'll name this tip to tip screw clearance. And I'm going to drop in the picture that we just copied. Now we're going to use this picture as the base of our loop diagram. Now anybody that doesn't know what a loop diagram is, it's really just a roadmap that's going to help guide our thinking and our calculations while we try to fill out our numbers. Now the first thing we want to do in a loop diagram is identify where the gap is. No, not smart art, the actual gap. So we're gonna start from one tip and show the other tip. Alright, so there we go. And we'll drop in an arrow on the top and also one on the bottom. And I'll name this the obvious name, gap. So here's our gap. Now when we perform our tolerance analysis, we want to start on one side of the gap and loop around to the other side of the gap. I prefer to start on the bottom side of gaps that are vertical or on the left side of gaps that are horizontal. That way up is positive or right is positive, just like we learned in school. Now if you decide to flip that around, it's up to you, but just make sure that you're consistent. So, like I said, we'll start at the bottom side of the gap, and we're going to loop around to the top side. Now, just like we used to sing as kids, you know, the hip bones attached to the leg bone and all that kind of good stuff, we're going to do something similar here. We can't just magically jump from the bottom screw to the top screw. We have to go through all of the proper connections or joints. So, the tip of the screw is attached to the head of the screw. The head of the screw is attached to the washer. The washer is attached to the bottom board. The bottom board is attached to the frame, and yada yada yada, all the way up and around until you get to the bottom side of the top screw. So we're going to follow that around, and it's good to use vectors to show what you're thinking about. So just like we started by singing the song, we'll go from the bottom side of the gap down to the underside of the screw head. The underside of the screw head is attached to the washer. So I'm going to go to the top side of the washer because the washer is attached to the printed circuit board. So here we go, we'll drop another vector in here. So if you look closely at what's happening, I've got a starting spot at the bottom. I've gone down, now I'm coming back up. And we're going to trace this all the way around until we get to the top side of the gap. So I'll copy a new line up here, pull in a new vector. So for those that are wondering how it is I'm copying these vectors so easily and stretching them so easily, when you try to drag these and make them a little longer, you're going to click on one end and not just drag it off to the side, but if you hold shift, it'll magically go back straight, and you can drag it up to however you want it. So then we go up to here. We'll go to the next board, and then to the second washer. Now from the top side of the second washer, we can go all the way down to the bottom or to the top side of the gap. Now I don't need to copy that one because I already have it. So we'll drop in our last vector. So if you notice here, I've got 1, 2, 3, 4, 5, 6, 7 vectors on here that make up this gap. That means I have 7 variables that build into determining what this gap is. So what I like to do now is go over to the calculations area and start to fill in descriptions of what each of these vectors is or are. So we'll start with the first one, which is this vector here that starts at the bottom of the gap going all the way down, and this we would lovingly refer to as the screw length. Now keep in mind we have 2 screws, so I'm going to name this one screw length 1. Then the next vector we have coming up from there is the washer, so we'll call this washer thickness 1. Then we go up through the thickness of the first board, so we'll call that PCB thickness 1. And then we have the thickness of the frame. There's only one frame, so we'll just call it frame thickness. Then we come up here, and that's PCB thickness 2. Then we have washer thickness 2. And then last but not least, we have the last screw length. So we'll have screw length 2. Alright, so now we have descriptions. We probably need to start filling in some values here. So the easiest way to fill in these values is to go and pull them from a detailed drawing, or if you have access to it, a model. In this case, we've got access to a model, so I'm going to go ahead and start pulling these mean dimensions from the model. So the first one I want is the screw length. So let's go back over to our model, and I can measure this. There to there. So we're at 250 thousandths. Come back to Excel, and I'll put in 0.250. Next one up is the washer thickness number 1. So we'll measure this guy out. Well, let me clear these out first. So from here to there, I have 32 thousandths of an inch. So we'll put in 0.032. Then we have PCB thickness 1. So we'll come over here. I've already cleared that one. How thick is that board? 98 thousandths. Seem to have lost my mouse. 0.093. Then we have frame thickness. Okay, mouse. Clear that out. And we'll go from bottom to top. 275. 0.275. Then we have PCB thickness 2. Now I know that this board is identical to that one, but for argument's sake, we're going to go through and quickly measure these last few and make sure that they are the same. So 93 thousandths, that looks familiar. This washer, 32 thousandths, I remember that number. And then the length of the screw, which was 250. Okay, so I believe that what we have here are identical parts. So 0.093, 0.032, and 0.25. Now, before I get too carried away, I want to make sure that we remember that we have to deal with signs. Now, I have my first vector up here. I'm going to compare this mean value to my first vector. So here I started at the bottom side of the gap, and I started moving down. So down, remember, is negative, so I need to put a negative sign in front of that 250. My next vector was pointing up, so positive is up. Here we have a positive value, and that washer thickness is okay at positive. Next one, PCB thickness, same deal. Positive, positive, great. Then we have the frame thickness, positive, great. This is up, up. Then we have a down vector, and that is the length of the screw, the second screw. So we need to drop in a negative sign there. So just like we did vector addition back in school, we can do that here. I'm just going to sum up all of these values. Now this is a simple 1D analysis, so Excel just saying sum is easy to do. So here we see we have a calculated gap of 25 thousandths, and it's a good practice to go in and compare what you've calculated to what you see in the model. So we see 25 thousandths, that's what we had. So either they're both right or they're both wrong, but either way, our numerical model matches our 3D model. So now we need to go and fill in some tolerances. Now, I'm not going to go through all of that going through drawings. That'll be for another tutorial. So for argument's sake here, we'll just use some assumed tolerances. So for a screw, we'll assume that that screw length is plus or minus, say, 10 thousandths of an inch. So we'll say 0.01. And I've got another screw down here, so this will be plus or minus 10 thousandths as well. Then I have a washer thickness. Washer, it's pretty thin. We'll call it plus or minus 2 thousandths. And I've got another one down here. I'll do the same. Then I have a PCB thickness. And PCBs, they're usually laminates and multi-layer and all this kind of good stuff. So they get a little more tolerance. We'll call it 10% or plus or minus 9 thousandths. Just for grins. And the frame thickness, we'll say that this is a machined frame, so we'll give it plus or minus 5 thousandths. Maybe you don't like my numbers, maybe you love them, but they're just assumptions. So here again, we're going to sum up our tolerances. And what we'll see is that we have a mean gap of 25 thousandths and 45 thousandths worth of tolerance. So we could calculate the worst case gap here, and we'll have a minimum and a maximum. So if you wanted to calculate the minimum gap, that would be the mean minus the tolerance. Very simple. If you wanted to know the maximum, that would be the mean plus the tolerance. And you'd say, oh man, I've got a negative value. The negative value represents an interference, or a potential for an interference. Some folks still use RSS, so we'll say what is the RSS minimum and maximum. And in order to calculate that, RSS stands for root sum squared. We're going to have to do a little bit of calculating. Now let me move my image over so that I can do some calculations here. So root sum squared stands or symbolizes the square root of the sum of the squares. So I'm going to square all of my tolerances. Oh, you don't like that. I'm sorry. I'm sorry. So we're going to square the tolerance, all of our tolerances, and then we are going to square root the sum of the squares. And this is going to give me the RSS tolerance. So I can figure out what is the minimum RSS gap, which would be the mean value, minus the RSS tolerance. I can find the maximum, which is the mean value, plus the RSS tolerance. Now, I don't like so many significant digits. A lot of them are really insignificant. So, we're going to make that a little bit easier to read. So we see the RSS gap is a little less extreme than the worst case gap, which is to be expected. Now, up until this point, we've just been kind of using QTA as kind of a formatting tool. But let's see what it can do for us. So if I go up here and click QTA, I can say Run Analysis. Now I've got all of these choices up here. I've got Monte Carlo, worst case, sensitivity, and RSS. So RSS, we know what that is. Worst case, we know what that is. Now I'm going to pick up sensitivity in Monte Carlo. So it goes off and it runs for a few seconds. Collects up some results. And lo and behold, we have a chart or some results. My mouse is going crazy. Sorry about that. So what we have here is some results that show the worst case minimum as a minus 22 thousandths, which matches with what we had calculated before. 72 for maximum, that matches. RSS 5 thousandths, that was the minimum, and the maximum of 45 thousandths. So all of those agree. We even have the RSS tolerance. But what we also pick up is the results from the 30 thousandths plus trials that it executed. And so we have a minimum value from all of those trials of, what is that, minus 16 thousandths, and a maximum of 64 thousandths. And we get the first four moments, or first four statistical moments from the analysis. So we requested sensitivity results. So what we get over here is a breakdown of which variables are impacting our gap the most and how much. And then we get a chart that shows where those results ended up being from the Monte Carlo analysis. So in fact, what we can do is we can take a screen capture of those results, paste them in, and we really don't need to go through all the headache of making those calculations and potentially screwing something up. We can just use these results. So thank you for watching, and feel free to add comments in the comment section. Don't forget to go online to QuickTol.com to download the tool. There is a free trial.